This is Physical Chemistry, Part 1, Thermodynamics, Chapter 5, Entropy and the second and third laws of thermodynamics. Section 5.1, The universe has a natural direction of change. A spontaneous process is a natural process. It takes place without effort or without external energy. For example, a gas expands against vacuum. This is a spontaneous process. Heat flows from a hot object to a cold object. Also is a spontaneous process. Can we reverse these two processes without external effort or energy? It's impossible. Can you imagine a gas shrinks all by itself and create some vacuum? Or can you imagine heat flows from a cold object to a hot object? Well, actually, this can be done, but you do need external effort. For example, an air conditioner, a refrigerator do transfer heat from a cold object to a hot object, but they both need electricity. External energy is required. The spontaneous process of an isolated system always leads to higher entropy. It also applies to the universe. So anything that happens in this universe is a spontaneous process because it happened. And it does increase the entropy of the universe, assuming the universe is an isolated system without external energy. Entropy is a measure of the disorder of the system or a measure of the extent of the energy dispersal. We'll talk about this later. Energy tends to be dispersed, and entropy tends to increase. The Boltzmann entropy has a very simple equation here. This is entropy defined by Boltzmann. It's equal to Kb times the natural logarithm of W. W is the measure of the number of microstates accessible to the system, and Kb is the Boltzmann constant. Kb is the ideal gas constant R divided by the Avogadro constant. So we have R here, we have this Avogadro constant here, and then K sub B, the Boltzmann constant, has a very small value. It's 1.38065 times 10 to the power of negative 23 joule per Kelvin. So how can we understand the number of states accessible to the system? Let me give you one example. When a dice is thrown, there are 6 possible states. The entropy is thus Kb times Ln6. When 2 dice are thrown, there are 36 states. 6 times 6. 3 dice, 216 states. That's 6 to the power of 3. So the entropy of 3 dice is 3 times that of 1 dice, because the logarithm of 216 is 3 times the logarithm of 6. So that makes sense. Entropy is an extensive property. It's proportional to the size of the system. 3 dice, well, you have 3 times entropy. The entropy of the universe keeps increasing until it reaches maximum. That's called heat death of the universe. The entropy of any isolated system cannot increase. Usually it keeps increasing until an equilibrium is reached. It's called thermodynamic equilibrium.